And so section 5.5, we move a little bit away from graphing stuff we've been talking about. We look at something a little different. This section is actually pretty easy. It has some different notation. Let's see. We've seen this before. This means the inverse, so the sine inverse, the inverse sine of root 2 over 2. So I could read this two ways. The inverse sine of root 2 over 2, or sometimes you'll hear that said the arc sine of root 2 over 2. Those are the same, mean the same thing, okay? So again, with that exponent -1, that's not actually to be interpreted as an exponent in this context. It's a superscript, okay? So I'm reading at that the inverse of the sine function. So what question is this asking me? This is asking me the opposite question as the sine function. So this is asking me what angle or what t value has a sine that is root 2 over 2. Okay, or in other words, the sine of what t value is root 2 over 2. All right, so I'd start this with just thinking about a unit circle, as you may have anticipated. Okay, so where is sine going to be root 2 over 2? Well, here and here. All right, so then what are my answers? I guess I'd have pi fourths, 3 pi fourths. Well, actually, couldn't I keep adding and subtracting 2 pi? Like just keep going around and around the circle again and again, and I'd arrive back at the same point. So I guess I would have 9 pi fourths, 11 pi fourths. I could even subtract, you know what I mean? So actually looks like I'd have an infinite number of outputs here. But you have to be careful. The key word here is function. Remember, in order for a relation to be a function, each input, so my input here, root 2 over 2, remember, that can have only one output. So the question is, how do I decide what the correct output would be? So as you might have guessed, the correct output, the one output I would choose as my answer would be this one, pi over 4. So I could think of that as the primary angle that has a sine of root 2 over 2. So what they did is they kind of came up with a standard. So we said, we want everybody around the world who calculates the inverse sine of root 2 over 2 to arrive at the same one answer. So we need a standard for how to select the one appropriate answer. So what we did is we said for inverse sine, we said the range, the output, we're going to choose the value between negative pi halves and pi halves. That makes sense because if I'm dealing with a unit circle, negative pi halves to pi halves corresponds with the right side of the circle. So you can see on the right side of the circle, every y value is achieved only one time. Okay, so if I choose that set as my range, I'm going to only have one solution. Okay, so that's just the standard. So I just have to remember, okay, when I evaluate the inverse sine, I have to go with the answer that falls in that set. Okay, so look at this next one. All right, so I start by thinking, okay, well, I mean, if I was to think about the whole unit circle, there are two angles where sine is root 3 over 2. So, I mean, looks like, again, I'd have a whole variety of answers. I could do 4 pi thirds, I could do 5 pi thirds, I could do negative pi thirds, negative 2 pi thirds, etc., etc. So, again, I can only have one answer because this is a function. So how do I make a decision? I have to look at my range. So here's my range of inverse sine. So first thing is, well, I know I'm going to choose the value, the point on the right side of the circle. So I know I'm interested in this point. But then I could see two ways right away that I could write that angle. I could write it as either of these. So which one is the correct way to write the answer? 5 pi thirds or negative pi thirds? Well, it would be negative pi thirds. So why is that? Well, I can think of it two ways. So one way to think of it is I have to be able to get to the angle without leaving the right side of the circle. So to get to 5 pi thirds, see how I'd have to go all the way over here? I cannot do that. The other way to disqualify 5 pi thirds is to think in terms of fractions. See how the range is values in between negative a half and a half pi? 5 thirds is not in between negative a half and a half. In fact, 5 thirds is a lot bigger than a half. It's bigger than even 1, right? So both of those are ways to conclude that the correct answer would be negative pi thirds. Okay, what about one with inverse cosine? So I can start out the same way. Okay, so now we're asking, where is cosine, the x value, root 3 over 2? So it looks like these 2 points. And then same idea where I have all these options for how to write these out. So I'm going to have to come up with a range for inverse cosine. So inverse cosine is different because if I was to choose the right half of the circle, actually, you see how x value would still be achieved more than one time? So actually that wouldn't work for my range. But what if I chose, say, the top half of the circle from 0 to pi? That's the standard, okay? That's like a definition. That's the standard range for inverse cosine. Because if you choose the top half of the circle, well, every x value is achieved only one time. Every x value between negative 1 and 1. Okay? So when I'm looking at my inverse cosine problem, the first thing I say is, okay, I know I'm interested in the top half of the circle. Narrows it down a little bit. Not that one, not that one. And then I say, okay, well, I have to choose the value that falls in between 0 and 1 pi. So 1/6 is in between 0 and 1. Negative 11/6 is, of course, not. Okay, so my correct choice is going to be negative pi sixths. These are my ranges. Okay, here's another one with inverse cosine. Okay, so I go, all right, I know inverse cosine. Interested in the top half of the circle. Where is cosine negative root 2 over 2? Here. So that would be 3 pi fourths. I double check. 3/4 is in between 0 and 1. In the correct range. I guess that's an easy one. And what about inverse tan? I have to extend this down. Okay, so two ways I think about tangent that I find helpful. One way is, well, we talked about graphing tangent. So let me just think for a second back to what the graph of that looked like. I had these asymptotes, vertical asymptotes at the pi halves. Then I had key points. This was pi quarters. This was 1. Something like that. So this is actually the graph of tangent, not inverse tangent. So when I'm looking at the graph and when I'm looking at this question, the question this is asking me, saying the inverse tangent of 1, is saying, tell me the angle, tell me the t-value that has a tangent that is 1. So if I'm actually looking at the graph of tangent, I'm saying, where on this graph is the tangent actually equal to 1? Isn't it right here? So that's where tangent is equal to 1. So isn't that at pi over 4? Okay. So it seems to me that it would make sense for tangent, or for inverse tangent rather, to choose the range to be in between those two vertical asymptotes. So actually this is the same as the range of inverse sine. It's the right half of the circle. It's just that you have to leave out the ends, right? Because tangent actually has those vertical asymptotes. So that would be one way to think about that guy. The other way would be, well, I mean, I could say, all right, when I'm going to find this inverse tan of 1, I could still think about the unit circle. I could say, okay, I'm looking on the right side of the circle. Tell me where tangent is 1. So in order for tangent to be 1, x and y would have to be the same, right? Because when I divide y by x, the quotient has to be 1. So indeed, I would conclude, oh, that would have to be pi over 4. So I can do the problem that way as well. So here are my 3 ranges. Those are useful. Okay, so what else is there? Oh, another one. Okay, inverse tan negative root 3. So if you try to do this one with the graph of tangent, so we're going, okay, where is, for which input is tangent equal to negative root 3? So I mean, I can see tangent's going to be negative over here. So I know my answer is going to be, I guess, somewhere in between negative pi halves and 0. But I can't really tell exactly what that angle is going to be. So I think in this case, it would be more useful to think about, okay, inverse tan. I'm looking at the right side of the circle. And then I'm going, okay, so tangent is negative. So I'm going to be somewhere down here. So I see that root 3 in there. So I really see 2 possibilities. I see this could be negative pi sixths. Let's write the terminal point for that one. Or it could be negative pi thirds. So I guess one way to determine which of those 2 that it is just to compute the tangent at each point. and see which one is negative root 3. So what would tangent of negative pi 6th be? So that would be the negative half over the root 3 over 2. Multiply by 2 over 2 would be negative 1 over root 3. Rationalize. Okay, so it's not that one. That's close. It's not negative root 3, though. It's negative root 3 over 3. Let me look at negative pi thirds. The y. Multiply by 2 over 2. Oh, look at that. That's the one. Okay, so this is the angle that gives me the correct tangent. So that means my answer would be negative pi thirds. Now remember, it would not be appropriate to write 5 pi thirds in this context, because to get to 5 pi thirds, I actually have to leave the right side of the circle, which I'm not allowed to do. So make sure you didn't write that. Okay, so those are the basics, and I mean, that's really the meat of this section. The other thing is, well, what about some compositions? So what if I compose, say, an inverse sine with a sine itself? So I guess I can do this the long way, and I could say, okay, first evaluate the inner function. So let's see here, what is sine of pi over 6? That's a half. Okay, now this is asking me find the angle on the right side of the circle that has a sine a half. Oh, the answer is pi 6ths. So it seems like I really did more work there than necessary. So, well, remember, inverse sine, well, it's the inverse of sine. So what do inverses do? They undo each other, right? So just as you may expect, I could do this problem by cancellation. Only thing I have to be careful with is whatever I get out of this ultimately represents a value of inverse sine, since that's the outer function. So remember, the range of inverse sine was negative pi halves to pi halves. The right side of the circle, okay? So yes, I can go ahead and cancel the sine with the inverse sine, so long as the result that I get out is in the correct range. So I have to go, is pi 6 in between negative a half and a half pi? Yes, a 6th is in between a half and negative a half. And indeed, you know, pi 6 is on the right side of the circle. So this is an easy one to do by cancellation. Okay, what about number 8? So same idea. The outer function is inverse sine. So the first thing I do is I say, okay, I need to determine the range of inverse sine. Well, I did that above, right? That's in between negative pi halves and pi halves. Okay, so I can go ahead and cancel. But then I have to look at what I get out. And I have to say, is this in the correct set? So is this in between negative a half and a half pi? Well, where is 3 pi 4ths? It's here. So that is not on the right side of the circle. Okay, so I need something that's on the right side of the circle. What I get is over here. So here's what I have to do. I have to say, which angle that is on the right side of the circle has the same value of sine? Okay, so I'm saying which angle on the right side of the circle has the same value of sine as 3 pi over 4? So the correct answer is pi over 4, not 3 pi over 4. And then indeed, I can check pi fourths is in between negative a half and a half pi. A fourth is in between negative a half and a half. So I have two options. I can either carefully cross this out, make sure I box this one. I can go back and erase that one. And then I can write that one as the answer. Let's try one with inverse cosine. So first step, look at the outer function. The outer function is inverse cosine. So whatever I get out of this, ultimately it represents a value of inverse cosine. Remember the range of inverse cosine? 0 to pi. It's the top half of the circle. Okay. All right, so then I can use my cancellation property. But I have to make sure what I get out, 2 pi thirds, to make sure two things. It's in the right part of the circle and it falls in the correct range. So 2 thirds is in between 0 and 1. So this guy works. That's an easy one. Let me try 10. Okay, first I look at the outer function. Outer function's inverse cosine. So again, I know the range of inverse cosine, 0 to pi. So I can cancel. Here's what I get out, 5 pi halves. So I have to check two things. So let me see if I count. Let's see. 1 half, 2 halves, 3 halves, 4 halves, 5 halves pi is here. So you're like, oh, well, that's on the top of the circle. But be careful because, yes, my point is at the top of the circle, but remember, I have to write a value that falls in this correct range. So 5 halves is 2.5. 2.5 is more than 1. So the other way to think about this is, remember, I have to be able to get to this point without leaving the top half of the circle. To get to 5 halves pi, I have to go all the way around. I cannot do that. Okay, so I have to adjust that answer. So I'm going to make sure I cross that one out, and I'm going to write instead pi over 2. That would arrive me at the top of the circle as well. And 1/2 is in between 0 and 1. Okay, so if you like, you can go back and erase that. And then you can move that. Or you can carefully cross out the incorrect value, box the correct one. Okay, what about these ones with tan? Okay, start by looking at my outer function, inverse tangent. Okay, so we talked about the range of inverse tangent. We said it was the same as inverse sine, but open parentheses because of the asymptotes. Okay, so I'm going well, I'm going to go ahead and cancel, right? And then I'm going to say, okay, the value that I get out, I have to make sure two things. is that on the right side of the circle? Actually, it is not. It's over here, isn't it? So now I have to say this. This is a little different. I have to say which angle on the right side of the circle has the same value of tangent as 7 pi sixths. Okay, so in quadrant 3 over here, x and y are both negative, so tangent would be positive. So the other place where tangent would be positive would actually be over here, because x and y are both positive in quadrant 1. So actually the correct value here is pi over 6. So actually tangent's a little easier, I think, because if you remember, the period of tangent is pi. So actually what does that mean? That means that tangent repeats diagonally. So points diagonally across from each other on the unit circle are going to share the same value of tangent. What's the difference with these? Be careful with these, because first thing I do is look at the outer function. Here the outer function is not inverse cosine. It is actually cosine. Okay, so I have to say, well, what is the range of cosine? Well, cosine spits out the x-coordinate of a point on the unit circle. That's one way to think about it. Or I can think about it as a wave, right? I mean, either way, the range is in between -1 and 1. So actually, these guys are the easier ones because I can actually go ahead and cancel so long as what I get out is in between -1 and 1. That is, I'm done. But you see something like this. The outer function is sine. So that's the y-coordinate of a point on the unit circle. It ranges from -1 to 1. But you see here when I cancel, I get 2. Okay? So that is not in between -1 and 1. So this value actually does not exist. And the reason why is because if you look at this inner part, this is saying, tell me an angle that has a sine of 2. Well, that's impossible, right? Because the biggest sine can be is 1. It's a 12. We try to write that. It's a 12. Tangent of inverse tangent of 12. Okay, let me think about tangent for a second. This is not inverse tangent, it's tangent. Remember what tangent looks like. Looks like that, right? Isn't the range all real numbers? So actually, these are the easiest of all. Because actually, since this guy can spit out any number, all I have to do is cancel, and I automatically have the solution.